All right, so let's look at this calculus problem. So this problem is from section 4.3 if you're in my surveyed calculus class. Um, and so we're finding where this function is increasing and decreasing. We're finding the max and the min. We're finding where it's concave up or down. And then I didn't look at this problem in weather sign before I started, but I imagine uh, we're graphing it, but probably it's a choose a multiple choice. But we will graph this by hand, and we'll see a couple of other. We'll need to find a couple other things besides what's required of us here. So first thing, let's find the domain of this function. So the domain of an ln function is 0 to infinity, not including 0. And then we also need to consider where the denominator is 0. That would only happen at 0, which is not in the domain of ln anyway. So the domain of this function would just be 0 to infinity, not including 0. Now, to get where we're increasing and decreasing, we need to find the first derivative. And so we're going to use the quotient rule. So the quotient rule, we have the bottom times the derivative of the top minus the top times the derivative of the bottom, and then all over the bottom squared. All right. Simplify this. X times 1 over x, we get 1 minus ln of x over x squared. And now we need to set that equal to 0 to find our critical points. Um, X squared is only 0 at 0, and that's not in the domain, so we don't really need to worry about that. Let's just solve 1 minus ln of x equals 0, and that, of course, we get ln of x equals 1, and so x equals e. So e to the first power is only critical value that we need to worry about. And so now let's put this on the number line. We can choose any point uh, between 0 and e, and we'll see if this function is increasing or decreasing on that interval 0 to e. So say we plug in 1. So f prime of 1 would be 1 minus ln of 1 over 1 squared, which is 1. And so ln of 1 is 0, so we end up with 1. So that is positive, so that tells us that we are increasing there. So increasing from 0 to e. And then let's find, so pick some number, we'll do e squared to make it easy. If you have a calculator, you can pick anything, but I don't have a calculator right here. So we'll just do f prime of e squared. So that's 1 minus ln of e squared over e squared squared, or e to the fourth. Now, obviously, have a calculator, it's not a big deal. But if you want to kind of save yourself time and not have to worry about mispunching things on the calculator that could cause you to get the wrong answer, we're really only worried about if this is positive or negative. Now, the denominator is always positive in this case. E squared or x squared is always positive. So whatever you plug in, the denominator is positive. So the numerator is what determines if this f prime is positive or negative at that value. So 1 minus ln of e squared is 1 minus 2. ln of e squared is just 2 over e to the fourth. So that's negative 1 over e to the fourth. E to the fourth, of course, is positive. So this would be negative. And so that means we are decreasing from e to infinity. Um, And so that's a pretty easy way figure out if it's positive or negative without having to use a calculator. You don't really we're not who cares what that value is. We know it's negative, and that's all we care about. So I think that saves you a little bit of time when you're doing these. And so we're decreasing there. And so this tells us without even doing anything with the max and the min, we at least have a maximum at x equals e. Now, what about vertical and horizontal asymptotes? And what about x and y intercepts? So those will be helpful. So let's find a vertical asymptote. How do you find a vertical asymptote? Set the bottom equal to 0. So x equals 0 would be our vertical asymptote. What about a horizontal asymptote? Take the limit as x goes to infinity or negative infinity, except negative infinity is not in the domain. So ln of x over x. Now, we're not really going to calculate this, but think about what you know about the ln function. The ln function increases always, but it increases slower and slower and slower, whereas x is like this. It's a constant slope, of course, but the further out you get, the bigger that distance is. So what you end up with is once x gets really, really large, you have some number, could be a big number. I mean, ln of x goes to infinity as x goes to infinity, but the bottom goes to infinity much, much faster. And so that limit goes to 0. So what do we have here? We are increasing up to e, and then we are decreasing. And we're going to approach the x-axis as we go out to infinity. And we'll be able to see that a little bit more clearly as we go along. What else we talk about? X-intercept. Now, of course, we have no y-intercept because x equals 0 is not in the domain, so there's no y-intercept. X-intercept, where is ln of x equal to 0? So to get the x-intercept, we need to set the function equal to 0. And for this function to equal 0, we really only need to worry about the numerator being equal to 0 because x cannot be 0 on the bottom. So as long as ln of x is 0, that quotient will be 0. So ln of x equals 0, that tells us that x equals 1. So we have an x-intercept at x equals 1. We have a vertical asymptote at x equals 0. We have horizontal asymptote at y equals 0. And then y-intercept, there is no y-intercept because x 0 is not in the domain. Okay, so now let's talk about concavity. So for concavity, we need the second derivative. So here's our first derivative. Let's take the derivative of that. So we have the bottom times the derivative of 1 minus ln of x. So that would just be negative 1 over x minus the top times the derivative of the bottom all over the bottom squared. So x squared squared, which is x to the fourth. And so let's simplify that. So x squared times negative 1 over x. That's negative x. And then we'll distribute, so negative 2x times 1 minus ln of x. So that's minus 2x plus 2x ln of x all over x to the fourth. And then combine our like terms, we get negative 3x plus 2x ln of x over x to the fourth. Now to find concavity, we need to set that equal to 0. And again, we really only need to worry about where the numerator is equal to 0. So let's say 0 equals negative 3x plus 2x ln of x. We'll bring the 3x over. Actually, probably what would be better is not doing that. Let's factor out an x. So if we bring the 3x over, um, not much we can do beyond that. So let's factor out the x. So we get 0 equals x times negative 3 plus 2 ln x. So now we know that x equals 0 is not a solution because x is not in the domain again, or 0 is not in the domain. So we need to find out where this equals 0. So negative 3 plus 2 ln x equals 0. 2 ln x equals 3. ln x equals 3 halves. And then we get x equals e to the 3 halves. halves. So there's our possible inflection point. And so let's test this. So e to the 3 halves. Again, pick a number, any number between 0 and e to the 3 halves. Let's see if it's concave up or down. So f double prime of, let's see, we could pick 1 again. So let's pick 1. F double prime of 1, we get negative 3. This term will go away because ln of 1 is 0, and that'd be over 1. So this would be less than 0. So we are concave down on that part. And then we can pick any number. Let's pick, again, we can pick something that works well with the ln. So let's pick e squared. So f double prime e squared. So we have negative 3 e squared plus 2e squared. Ln of e squared would be 2. And then over e to the 8th, which again, it doesn't matter what is on the bottom because the bottom is always positive. So we're really just worried about what's the sign of this numerator here. So we have negative 3e squared plus 4e squared. That's going to be positive. So we have concave up over here. Okay, so that's a lot. And so let's get another page here and we'll look at the graph. So I have all this summarized here. So we have increasing from 0 to e. We have decreasing e to infinity. We have a maximum at e, and then the y value is 0.368. Not super important. No minimum. And then we have concave up from e to the 3 halves to infinity, concave down 0 to e to the 3 halves. And it's about 4.5. So that makes it easier to draw on the axis here. Then we have an inflection point. So because it changes concavity at e to the 3 halves, that would be an inflection point. We have a vertical asymptote at x equals 0. We have an x-intercept at, we said 1, 0. And then horizontal asymptote, we have to write that, y equals 0. Okay, so now we just need to kind of get these points. So what I do when I'm doing these graphs, plot the points that we know. So we know that, so let's do 1, 2, 3, 4, 5. I think that should be enough. So we know that we have a maximum at E, comma 0.368-ish. So E is 0.271. So let's put that here. So we have a maximum there. And then we are concave up. We also need 4.5. So 1, 2, 3, 4. Let's put something there. And then we have an inflection point at 0.33 right there. Okay, so now kind of what I do, I make this little chart and I put these particular x's in here. So e and e to the 3 halves. So the kind of the critical points. So we have the critical point for the increasing, decreasing. We have the inflection point. And then anything else, if you had a vertical asymptote somewhere in the middle of the domain, that would be important to put. And then we can plot this x-intercept. That's another one we need to plot. So let's plot critical points, inflection points, and intercepts. And then once you do that, let's talk about the shape. So actually we probably need, let's erase this for a second. And then let's add another column here. So we need to put 0 in here. So let's put 0. We'll add another column here. Let's put 0, actually 0 to E. e to the 3 halves, and then e to the 3 halves to infinity. So these are our intervals where things change at these endpoints or possibly change. So we're the derivative, first derivative is positive between 0 and e, positive. And then the first derivative is negative after e, so negative, negative. All right, so 0 to e, we're positive. After that, we are first derivative is negative. Then second derivative, concave up after e to the 3 halves. So concave up would be positive, concave down before that. And you can kind of do these, you can put these rows in any order if you, whatever order you like. So now by shape, what do I mean? So in this interval, we are increasing and concave down. So what does that shape look like? That looks like that. So between 0 and there, we are concave down and increasing. So it's going to look like that. Between e and e to the 3 halves, we are decreasing, concave down. So let's write this here too. Increasing, decreasing, decreasing. So that's what the first derivative being positive or negative means. Second derivative is negative, concave down, second derivative positive, concave up. So decreasing and concave down, that looks like that. And then we have decreasing and concave up. Um, that looks like that. Okay. So now it's really just a matter of using these shapes to connect these points. Um, so between 0 and e, we are concave down. And of course, you got the vertical asymptote like that. So it's not going to cross the x-axis. Of course, it's not going to anyway because of the domain. Then after e, let's put that there, e to the 3 halves. Between e and e to 3 halves, it's going to look like that. So we're going to connect these like that. And then after that, it's going to have this little concave up, but decreasing. And of course, we have the horizontal asymptote at y equals 0. So we're not going to go below this. We also know that because the only x-intercept is at 1. So it can't cross again because that would be another x-intercept. So let's draw this kind of like that. It's not touching the asymptote. Okay. And that's what the graph looks like. So this is a lot. I would suggest when you are doing these problems, have a process for doing this. Like you, step one, and you do these in different orders. Step one, find where you're increasing, decreasing. First derivative, increasing, decreasing. Step two, second derivative, concave up or down. Step three, find your intercepts. Step four, find your asymptotes. Step five, make this little chart. Or step five, maybe plot these points. Step six, make this little chart. And then step seven, draw the graph. So it does take practice a lot. If I do this in a classroom, it takes up the whole board all the way across. So if you got any questions or comments, you can leave them. If you have other problems you want me to do, you can leave those in the comments as well. So hope you all have a great day.